Oblique wing just means that the wing is at an asymmetric angle to the fuselage. And it was a very low-cost, short project. We were done by 1981. We had all the research data already. But the idea kept coming up in the course of my career the whole rest of the time. So I have a kind of a unique perspective on oblique wings. So I thought I'd share that and also kind of give some history of the concept and try to explain why anybody would be interested in oblique wings at all. And so with the history, I think most people in this audience will not be surprised to learn that the first use of oblique wing was by the German engineers during World War II.
Yes.
Okay, so I worked at NASA pretty much my whole career, and almost all of it was at the Armstrong Flight Research Center. It used to be called Dryden, and it's the smallest of the NASA centers, located up on Edwards Air Force Base, so kind of a remote location. It's always the center where NASA did its exotic or one-of-a-kind research flight testing, and it dates all the way to 1947 when it conducted the supersonic research and the rocket plane studies. It was the site for the X-15 flight tests. The space shuttle landed at our center in the development flights. And I was the aerodynamics branch chief for about 15 years. And during that time, especially, and almost all the time, in one way or another, you work on almost every project at the center. But the first project that I really worked on from start to finish was this oblique wing research airplane. And oblique wing just means that the wing is at an asymmetric angle to the fuselage. And it was a very low-cost, short project. We were done by 1981. We had all the research data already. But the idea kept coming up in the course of my career the whole rest of the time. So I have a kind of a unique perspective on oblique wings. So I thought I'd share that and also kind of give some history of the concept and try to explain why anybody would be interested in oblique wings at all. And so with the history, I think most people in this audience will not be surprised to learn that the first use of oblique wing was by the German engineers during World War II. And in the US, it turns out to be Dr. R.T. Jones. And he is one of the preeminent aerodynamicists of all times. He is, like a lot of geniuses, has a real colorful history. He started out in a flying circus, ends up operating an elevator in the congressional office buildings, learns engineering at a junior college, and is picked up by Max Monk as a budding genius and brought into the NACA. And he's a big part of the team by the start of World War II. Anyway, he is credited actually with developing the underlying theory for swept wings in general, not just oblique wings, but all swept wing aerodynamics. So you can see a very influential person on airplane design. In addition to that, he was made contributions to delta wings, tailless airplane control. He worked on telescopes, designed telescopes. He did the fluid analysis for the first artificial heart valve, and he made violins in his spare time. So really diverse person, a lot of capability. Anyway, as after the war, as interest really picked up on developing practical supersonic aircraft, Jones pointed out that a sweep is very important, but if you really want the ideal configuration, you'd like an asymmetric swept wing. And so at this point, let me switch over and talk about why that is. Why is an oblique wing actually preferable? And, as you do start to approach the speed of sound, there's a lot of challenges. The stability and control changes dramatically. Propulsion is more difficult. But as much as anything, the drag on the airplane increases exponentially as you approach the speed of sound. To just explain this a little bit, if you take the drag on any airplane and if you divide it by the dynamic pressure or the square of the velocity, you come out with a drag coefficient. And that coefficient is pretty much constant at any speed, all the way until you get close to the speed of sound. And then you have an entirely new component of drag due to compressibility and the formation of shock waves. So this gets called out as wave drag. And, designers, you could recognize that quickly. People kind of saw it as, it's the price of going faster or the penalty you have to pay. But a different researcher came up with a fairly simplistic way of understanding this wave drag component. He was Dr. Whitcomb at the NACA Langley laboratory, and he saw that wave drag is really proportionate to the rate at which cross-sectional area changes along the length of the fuselage. So let me show that graphically. It's actually pretty easy to understand. If you take a typical supersonic airplane and take a slice across it and look at the cross-sectional area, you've got the area of the fuselage, the wings, and the tails. If you plot that out along the length of the fuselage, this area grows and grows, and this is what would be bad from a area rule perspective. But once you recognize that, you can accommodate it, and in this case, if you neck in the fuselage to accommodate for the wing area, you can flatten out that area distribution. And this is a great improvement for wave drag. This particular example is kind of neat for the San Diego area. This is the F-102 prototype on the left. The prototype was being built in San Diego as Whitcomb was developing this theory. And the engineers had already seen, it was going really bad. They were expecting, and in fact, the flight test of the prototype showed, it would barely go supersonic. And this was supposed to be the country's first supersonic fighter. And so it was going to be a real failure until they were able to collaborate between NACA and Convair, incorporate this Coke bottle shape to the fuselage, which greatly improved performance. It saved the program, and it's really a pretty subtle change, between the two airplanes, and yet that modification to the fuselage increases the speed of the airplane by 25%. So a really dramatic improvement, and it's kind of a great example of where theory can really change the real world, and especially it'll come up with solutions that you would never anticipate or come up with by trial and error. So kind of a neat example, but if you understand wave drag in this way, you see that symmetric wings have a fundamental problem. As you sweep them aft, the cross-sectional area is going to grow along the length of the airplane. On the other hand, if you sweep one wing forward and leave the other aft, now you smooth out that cross-sectional area along the length of the airplane. This is the ideal wave drag configuration for high-speed flight. There's another aerodynamic advantage. If you think of the wing, kind of the way the air does, it's going to set itself up in a pressure field, and we can see the pressure field by lines of constant pressure, isobars. And of course, the pressure field isn't going to come to a sharp point at the center line of the fuselage. Instead, the center inboard region of the wing is going to see, it's effectively at a lot lower sweep than you expect it to be, which is a big loss of efficiency as well. And it's something that an oblique wing doesn't have. The pressure field moves right across the center line of the fuselage. So a couple of really good aerodynamic advantages, but there's some other advantages if you have a need for variable sweep. And I think most people know that an unswept wing is ideal, has the best lift-over drag for low speeds, but it drops off badly as you go faster. Swept wings are good at high speeds, but they work poorly at low speeds. So you'd really like to have a variable geometry where you get kind of the best of both worlds. And the F-111, the F-14 all took advantage of this, but you don't see variable sweep on a lot of airplanes because it comes at a very high price. You have to carry these. You have to carry these wing pivot structures, very heavy, and you're moving the whole wing structure, all the wing components, and not only that, this becomes a flight critical system. It's got to work every time the pilot commands it. It's a complex maintenance item. So you can see right off that an oblique wing has an advantage that, it's only got one pivot instead of two of them. But it's actually better than that. If you look in the details of what's going on at the pivot, the wing generally creates the lift, and you end up with a bending moment that has to be transmitted into the fuselage right where this pivot is. So you're transmitting all of the wing lift through the pivot itself. Now, if you have an oblique wing, you've got a continuous wing spar, and you don't have to resolve that root wing bending moment at the pivot. So it only has one pivot instead of two, and the pivot itself is a lot lighter weight, a lot simpler design. So this is a really important advantage if you need variable sweep. Another nice feature about it, if you have a symmetric swept wing, when you move the wings back, they also move the center of lift back. And so you got to be prepared for a big trim change. Some of these airplanes, they move their fuel around to accommodate the change in trim. Some of them have a massive elevator, horizontal tail. Again, oblique wings don't have that problem. The center lift stays put when you sweep the wing. So, with all of these advantages, now you're probably thinking, why doesn't every airplane have an oblique wing? Until you go back and look at it and say it really is a very strange shape. It's unusual. And, of course, that perception is very important, especially if you realize that one of the big applications for this has been as a passenger supersonic airplane. And it's a fair question, would passengers really pay to fly on something that is that unusual? And, I think a pushback to that, though, is that, we're not looking at small improvements. These lift to drag improvements and such are, it's not nickels and dimes. If you had this, you could potentially offer airfares that are like 25 or 30% lower than your competition. And so, if you had that kind of savings, I think people are probably going to overlook the fact that their airplane is peculiar. But maybe more important is, the old saying that, if an airplane looks bad, it probably flies bad. And indeed, this does have some challenging flying characteristics. As you would expect, if you pull back on the stick, the nose does come up, but at the same time, it rolls off to the right. And if you step on the rudder, the nose pitches up or it pitches down. So, bad cross-coupling aerodynamics, nothing good about that. Again, I'd say that, when this was first being taken seriously at all was the 1960s. And by then, it was already pretty clear that every high-speed airplane was going to have flight control computers and be able to accommodate some of these kind of problems. And, of course, that's been the case. Modern flight control systems can mask a lot of those problems. But they are significant issues, and so you end up with this problem that it's a very attractive idea, a lot of potential advantage, but at the same time, a lot of technical risk. And so there was a lot of effort made to try to quantify, how bad is bad and how good are the benefits. The picture at the lower right there is probably one of the most sophisticated unmanned airplanes of its time. Chuck Dorgan showed me a picture of it in the Udvar Hazy Museum, but it's a oblique wing model airplane in the early 70s. But basically, all this research became much more focused as interest in the supersonic transport really picked up. And, the first generation of supersonic transports were the British and French Concorde and the Russian Tu-144, incredibly sophisticated airplane for their time, and even by today's standards, really remarkable capability. The U.S. was also engaged in supersonic transport development, but the U.S. was coming late to the game, so to speak, and so it really had to have a more capable vehicle. Couldn't really compete with Concorde directly. It had to be, if it was going to find a niche, it had to be quite a bit more capable. And so the U.S. designs were much bigger. These are just scale models, of course. But, the U.S. design was going to carry twice as many passengers and go quite a bit faster. Some of the U.S. designs were going to go Mach 3. So it was a real technology push, and the U.S. approached it with a design competition, down-selected in 1966 to a Boeing configuration that actually had variable sweep wings. And again, for a passenger airplane, that's a pretty aggressive idea. After the down-select, they eventually gave up on the variable sweep, went to a more conventional configuration, but the whole program was canceled in 91, and the reasons for that are complicated. It's a whole nother presentation in its own right. But it kind of mentioned this a lot. I include this mostly for other audiences where you're trying to convince people or remind people how serious the SST program had been at the time. A lot of people today really have no concept of it. And, of course, in the 70s, the expectation had been, we'd all be flying supersonic airplanes across the Atlantic. Certainly by the 90s, airlines were adjusting their fleet mix. They were looking at, offloading their subsonic airplanes. And so it was a real change in philosophy, a real change in aviation history. But it kind of explains why so much attention was being given even to things like the oblique wing. It wasn't like this was going to be the U.S. competition, but it was obviously a really viable supersonic concept, and everybody wanted to know more about it. So NASA actually continued funding the oblique wing even after the SST was canceled. They kind of wanted to get the technology to a good stopping point so that when we returned to SSTs, you'd be able to pick it up. They also find things about the oblique wing that would have solved some of the challenges for Concorde or the conventional SST. So it led into a pretty... So they had a pretty sophisticated contractor study. NASA had Boeing, do a side-by-side comparison of conventional configurations and a couple of oblique wing designs. They traded off all kind of things like the engine placement, whether you yaw the horizontal tail. And they found some pretty interesting conclusions. One was that, an oblique wing could probably fly Mach 1.2 over land without a sonic boom. And even if you weren't allowed to go supersonic, the oblique wing can unskew itself and still be a pretty efficient airplane, even subsonically. And this was one of the things that really killed Concorde. It could fly very efficiently across the ocean, but when it had to decelerate to fly over land to Dallas, it becomes very ineffective. So anyway, some really attractive benefits. They found the single oblique wing fuselage configuration here was the winner. And NASA at that point had a little more money to be able to explore a low-speed flight project. There wasn't any money for serious supersonic research at the time, and no way to do a high-speed test, but we were able to build this AD-1 demonstrator, and it stands for the Ames Research Center and the Dryden Research Center working together. And that was just about the time I joined NASA, and it was just at the right time. It was a great partnership. We did the wind tunnel testing at Ames. We had to find a designer who would do a one-off, low-budget, minimal investment sort of project. And one of our engineers had gone to school with Burt Rutan. And Rutan was fairly well known at the time, having built the Very Easy at that point, but it was before Scaled Composites was formed. And he did this detailed design for the airplane for about $250,000. We had a small company in New York actually build the airplane, also for about $250,000. The engines cost about $40,000, so you ended up with a manned jet, one-of-a-kind research airplane for barely $500,000 overall. And it was neat as a very small project, very simple, no flight control computer, just control cables and pulleys between the stick and the surfaces. The wing sweep was this toggle switch on the panel. If you held it to the right, the wing would sweep at about 3 degrees a second. If you held it to the left, it would stay put and the wing would go back to 0. But you get to talk about, really, long range ideas like, the thinking is, there could be fleets of these airplanes built someday. And so you ask, do you want to have it go right wing forward or left wing forward? And it doesn't really matter, except that, if you do it, you would hope everybody would do it the same way, kind of like driving on the right or left side of the road. It doesn't matter which way you do it, but it's nice if everybody does it the same way. So we picked right wing forward because we were thinking, the thinking was, if it's a supersonic transport, you'd want to load passengers from the left side of the fuselage in the front, so you could sweep the wing and pull up to existing passenger gates. We also talked a lot about what do you want to call the angle. It was called the yawed wing, the scissor wing, the skewed wing, the slewed wing. And we liked skew angle because that implied that it was not symmetric. But and we actually put that on the instrument panel, but really everybody has always really just called it wing sweep. But some things you can't control very well. But our project pilots were Tom McMurtry and Fitz Fulton, and they were, well known from many prior projects. At the time they were doing this project, they were also the crew of the 747 from which the space shuttle was being launched, or the ALT flights were being carried out. And anyway, great pilots. They made flying the airplane look actually kind of easy. I flew the simulator. It wasn't very easy to fly, but and also very easy to work with. Just humble, great people to get to know, especially as a young engineer who, often made a lot of mistakes. They were very easy to get along with, and helped out a lot in every way. So we took a good while expanding the envelope. It took about a year to get all the way out to 60 degrees wing sweep, but we collected data almost every flight condition, and like I say, it has unusual characteristics. This is a rolling moment due to angle of attack. And, normal airplanes don't have this kind of characteristics. And it had, pitching moment due to elevator, pitching moment due to aileron, and it had yaw due to pitch, all kind of strange characteristics. It had a trim requirement. If you were flying the airplane at 60 degrees sweep, you had to either have the, some bank angle, or you had to yaw the nose off to the right, or have some combination of the two. So it's unusual flight characteristics. but of course we expected that, we also took pilot ratings. If you're not familiar with them, pilot ratings of 1 or kind of normal as you'd like it. A rating of 10 is really bad. You're almost very poor characteristics. And surprisingly, the airplane rates quite acceptable all the way up to 45 degrees wing sweep. And then it deteriorates badly beyond that. It rolls easily, very low rolling moment of inertia. Again, nothing we didn't expect, but what we could do was then take the aerodynamics that we measured, build it into a simulation, and do studies to show that, a pretty reasonable approach with a flight control computer can handle a lot of the problems. So the project, we collected the data, and it was pretty positive. We, at this point, nobody was interested in a supersonic transport, but we wrote reports and put them on the shelf, and we're kind of moved on to other work. And we're really surprised a few years later that there was a whole other customer, and somebody who was not what I would have expected. It was the U.S. Navy, and so now the Navy is now interested in a whole different application. And I don't really have a military expertise, but the way they described their problem, this was the early 80s, and they were seeing the threat of cruise missiles against their carrier groups. And at the time, saw cruise missiles as maybe 100-mile range, but they were seeing that growing to maybe 1,000-mile range. And so they were interested in a fleet defense airplane that would have replaced the F-14, but they needed it to be able to dash out 1,000 miles and then loiter for a long period of time, engage the enemy, and still get back. So they weren't really that interested in aero efficiency as much as they wanted a wide range of performance, high speed and low speed capability. So they did a pretty serious design study of this airplane here, the one that's in this configuration. And their biggest concern was, of course, still nobody had ever seen a high-speed oblique wing flying. So they proposed a partnership, NASA, Navy, and would modify an F-8 with an experimental oblique wing. And this was really going to be a great project. And, we had really got a chance to work with people from all over the country, especially the Navy, which was kind of it's a different culture, different organization, different aero expertise. And, you see things differently. They looked at it and wanted the left wing to go forward, thinking, of course, that if you were going to launch the airplane swept, then you'd probably want the right wing swept aft so that it wouldn't block the pilot's view of the catapult operator. But, they actually went with our plan to do it right wing forward just because we already had data. They didn't want to confuse the mix a little bit. The other thing that Navy picks up on immediately is, this airplane, you could fit a lot of them on the deck of a carrier. If you over-skew the wing, you could park them practically side by side on an aircraft carrier. And, it's one of those things, NASA would never have thought of that. And yet, it's a huge issue for Navy. So anyway, we worked 2 years on it. We made great progress in the aerodynamic modeling, had a lot of control system to work with, research, developed an aeroelastic wing design. We had an airplane for it. It was an F-8 that had already been used for flight controls research. It was the first airplane that was ever flown with fly-by-wire in all 3 axes. So it had these digital computers that we could have modified with the flight control laws. The F-8's also kind of nice because you can remove the whole wing as a unit and add this experimental oblique wing. But it was all, going fine, except that the Navy eventually had to pull out, mostly because they were seeing cost overruns on other projects. And very disappointing, but it's not unusual for, flight research projects. It was, we kind of, again, wrapped up the work. However, some of our colleagues at NASA Ames continued working on oblique wings after that. And one of the things that we had found with the F8 project was that a lot of the challenges came from the interference between the oblique wing and the fuselage. And so you can fix that, of course, if you get rid of the fuselage entirely. And this was a design drawn up, again, by Dr. R.T. Jones, who is now working at Stanford. He's in his late 70s. And so he comes up with the idea of an all-wing oblique transport. And this actually triggers another flurry of research. And it was a great combination of NASA Ames, Boeing, Douglas, and several universities all did designs on this all-wing passenger transport idea. And they looked at different control locations, engine placement, and gear, and a whole lot of really good work was performed. They did a lot of wind tunnel testing again. And there's a lot of reason to be interested in this. If you like flying wings, to begin with, there's a lot of advantages, of course, to flying wings. If you don't have a wing tail configuration, you get structural advantages by spreading the span out along the load out along the span. You don't have skin friction drag or profile drag from the fuselage or tail. And so there's almost no way around it. You're going to end up with a much more efficient airplane at all speeds. Even, clearly it's going to be dramatically better than even a 747, which is already a very good airplane. But the very same airplane could then go out to high speeds and be more efficient than any supersonic transport you're going to find. So it's a really compelling idea. The biggest challenge to it is just the overall geometry. If you're going to make this wing big enough so that you can stand up in the wing, and you're also going to have an airfoil that you can fly at high speeds, there's no way around it. This ends up having to be a very large airplane. And all of these designs we're looking at, they're on the order of like 400-foot span, 400-meter span. I mean, these are big airplanes. And, not 400-foot span, I'm sorry. And, big enough that you'd have compatibility issues. You could land them on existing runways if you landed them at about 30 degrees. But no doubt about it, you'd have to, modify airports to handle them. But this was not as crazy as it may seem, because this was the mid-90s, and really it wasn't clear at that time where airliner design was headed. At the time, Boeing was still considering a mega transport, something twice as big as a 747 perhaps. Airbus had not committed to the A380, and Airbus was looking at things like blended wing bodies, other kind of radical configurations. So, a big flying wing really didn't stand out as being that unusual. Some of the other challenges the oblique wing had was there's a lot of volume in a wing this size, but it's still kind of difficult to really fit a passenger cabin into it. And the passengers end up sitting not facing the direction of flight, either for takeoff or landing or some combination. The floor is going to bank a little bit, different flight conditions. So there are challenges, nothing that can't be solved, but it was kind of neat that we had Boeing and Douglas participating in this, to kind of put some realism into it. But again, that was the biggest drawback, and nobody was too serious at the time of moving forward with something to kind of put some realism into it. But again, that was the biggest drawback, and nobody was too serious at the time of moving forward with something like this. And certainly by the late 90s, it was becoming clear that, airplanes weren't going to keep getting bigger anytime soon. And both companies have now headed more toward large twin-engine airliners, more conventional sizes. So again, this is kind of on the shelf. All the data was put out in public domain, ready to go, and maybe there'll be a future for this in the future when big airplanes are needed again. Anyway, I'll just touch on a couple other things that came up over the years. One of the costliest aspects of the space shuttle program was trying to recover the solid rocket boosters. They'd parachute into the ocean, they'd have to be floated, towed back into the Cape Kennedy, exposed to salt water. And there was always ideas out there for how to fly these boosters back to the launch site. But Ames looked at using the oblique wing. You could stow it completely for takeoff, for launch. Then you could use a high-speed setting for gliding back to the mainland, and then sweep it to zero sweep to land on the runway. Like I say, there were a lot of proposals. This is the only concept that would have worked without having a engine installed on the boosters. So, really, really cool idea, but, the shuttle flight rate never got to the point where, once it started to be clear it wasn't going to have a high flight rate, nobody was going to pursue these kind of development. But, and then one last study came up. DARPA got interested in oblique wing from an uncrewed military perspective. And they did a study project with Northrop to look at a fairly large airplane that could do deep penetrations, high-speed combat airplane, fly Mach 2 deep into foreign territory. And again, I got to consult with the aerodynamics on this, but was not really a part of the team. So and the results of this would be classified. But DARPA didn't pick up on the phase 2, the flight test portion of it. But anyway, like I say, the concept has come up numerous times over the years. But at the end of the day, this is 40 years later, and the 81 is still the only piloted oblique wing that's ever been flown. And small $500,000 airplane still gets a lot of attention. And, you continue to see ideas come up over time. And, for everybody, all the people who've worked on it, I think all of them would probably agree that, you wouldn't really be surprised if there's going to be an application someday for which oblique wing is really the right answer, and you might see it in the future. So anyway, that's my talk. There I am in 1980. We were a real small project team, not this small by any means, but I got to work on this as one of 2 aerodynamicists, did all the data extraction for the aerodynamics on it. So anyway, there's my talk. If you have any questions either here or anytime, I'm always love to talk about the oblique wing.
Question, and I don't know if you stretched the flight envelope out to this, but how did that thing stall?
How did it
Stall? What were the stall characteristics?
Oh, stall characteristics. It would stall left wing first. In general, as you pull back, the left wing, the downstream, the aft swept wing loads up quickest, and indeed it does stall first. In some ways, there's some advantage to that in that before it would really spin, it tends to roll off, and so we never did. It never got into any kind of spin or anything, but it would stall asymmetrically.
Thanks, Bob. That was an excellent presentation.
Thanks.
Bob, can I ask you a question too? If you were to apply a swept or an oblique wing concept to a conventional airliner, a subsonic airliner, would those speeds, when you get to your Mach compressibility, would they be much faster than the current 8.2, 8.3 rate they were flight in?
Yeah, one of the things I couldn't mention here was in the early 70s, when they did these contractor studies, actually one of the studies was focused on applying oblique wings to subsonic applications. And Lockheed did that study, and I've got the drawings for it if you want to see it sometime. It looks like a C-5A with a oblique wing. They have a TriStar looking configuration with a oblique wing, and the idea is they would go up to about Mach 0.95. And again, the thinking was at that point, of course, you wouldn't be able to fly supersonic over land, but here's still a lot of value to it. They actually, one of the features they pointed out was, this was the first fuel crisis, and they were saying, here you could have a variable sweep subsonic airplane, and you could pick your speed based on the price of fuel. If fuel was cheap, you could sweep it all the way and go Mach 0.95. If the price of gas was up, you could unsweep it and still be pretty efficient at 8 tenths or 7 tenths Mach number. So yeah, a lot of interesting applications there too.
Thanks.
Hey Bob, Dave Barnett, I have a quick question. I've heard about the quiet supersonic. I believe it's the X-59. Do you know what the status of that is these days?
The X-59?
Yeah.
Yeah, it's being constructed at Dryden right now. I know it's actually being constructed in Palmdale, but the engines pieces have been delivered to Dryden right now, and I forget what the flight schedule is, but of course it's trying to demonstrate a low boom flight conventional configuration, which they've kind of demonstrated in pieces. They've demonstrated reducing the nose shock, the inlet shock, the tail shock, but they needed to have, the desire was to have a research vehicle that would put them all together simply for the purpose so they can take it around the country, fly it over real communities, and get community feedback and concurrence that the shock wave is not upsetting, and encourage the FAA to change the rule.
Thank you.
Yeah. The real challenge for probably one of the big mistakes in moving away in the 70s was that the FAA, when they did decide to take the sonic boom issue seriously, they really just set up the rule that you can't fly supersonic over land. And they should have made a rule like you can't create an annoying sonic boom over land. And so the thinking is that they have the technology to do an acceptable boom over land, but nobody will invest in it because the FAA rule says that, you're just plain prohibited from flying supersonic. And so they're trying to get the FAA to change that rule.
Great, thank you.